Now we want to talk about the electric field. Let's begin by reviewing what a field is. It's simply a function that takes a value at every point in space. So for example here, what we essentially have is a map of the United States showing the temperature field. In different colors it shows the temperature at different places. Every place across the United States has a temperature, and we simply code this with the value at each different point. So some of these places are in the 60s, some of these places are in the 40s, some are very cold indeed in the 0s, 10s, and thereabouts. So that's a temperature field. Now we can also deal with vector fields. For example, in 101 we talked about a gravity field. We know that if I have an object near the Earth, that object will feel a force. But if there's no object, say over here, then does there still exist anything? We know that if we put an object there, we will have something. And we know that the force on any object we put there will be proportional to the mass. So we like to define something that is the force per unit mass, and we call that the gravitational field. In the case of gravity, it has the additional meaning of being the acceleration at any point due to gravity. But in general, it's the force per unit mass. Okay. So if I want to map it out, all I would have to do is come to a point and measure the force at that point. And then I would take the force, divide it by the mass of the object I'm testing with, and I would set that equal to my value of g. It wouldn't matter if I used a bigger if I used a bigger mass, because a bigger mass would simply get a bigger force, but when I divided the force by the mass, I would get the same value for g. And as I mapped it out, I would find that the gravitational force everywhere pointed inward towards the center of the Earth. And I would find that as I came further out, the force got smaller. All right, so that's the gravitational field around the Earth. The force is larger inside, so the gravitational field is larger. The force is smaller further out, so the gravitational field is smaller. We do something similar with electric fields. We know that there will only be a force on an electric charge if there is another charge there. So I've got a source charge here that can exert a force on other charges, but it will only exert a force if I put another charge at one of these different places. However, something exists due to this charge, even if I don't have the charge there, the second charge. How do I figure out what that something is? Well, I take a small charge, I stick it here, and I measure the force on it. Now the force will depend on how big of a charge I use. I use a small charge, I'll get one force. I use a larger charge, I'll get a different force. However, if I take the force and divide it by the charge, I'll get the same value, which I'm going to call the electric field, for whatever charge I use here. Just like in the case of gravity, I got the same value for any mass that I used, and that was my consistent gravitational field. I get the same value for any charge I use to test the electric field around this charge. Okay, a few caveats. When we tested the gravitational field around the Earth, we wanted to make sure we stuck with test masses that were much less than the mass of the Earth. We don't want to mess up the motion of the Earth with our test mass. In the same way, anytime we test electric field, we want to make sure that this test charge is small enough that it doesn't cause the source charges to move around and significantly alter the electric field. Alright, so the electric field is the force per unit charge, and the units of that are generally, units of force are newtons, unit of charge are coulombs. So the units of electric field are newtons per coulomb. We could have done something very similar with gravitational field and said that its units were newtons per kilogram. Now it happens that a newton is a kilogram meter per second squared, so a newton per kilogram is also the same as a meter per second squared. But when we're thinking of it as a gravitational field, it's often useful to think of it as a newton per kilogram. It's something that causes a force when we put a mass there. So this chart just shows typical values for the electric field at different places where you might test it. We have at the surface of a uranium nucleus, it's about 3 times 10 to the 21 newtons per coulomb. About where the electrons are in a hydrogen atom, it's about 5 times 10 to the 11 newtons per coulomb. One thing you might notice, you couldn't directly test this because you would never have a charge that was much smaller than the source charge. The source charge in a hydrogen is just 1 proton. That's 1 fundamental electric charge. The smallest thing we could test with would be 1 fundamental electric charge. But we can still calculate the electric field and have some meaning. On a nerve cell membrane, it's about 1 times 10 to the 7, so 50,000 times smaller. Electric air breaking down, a lightning bolt, a spark, that's about 3 times 10 to the 6th, so in other words, about 3 times smaller than on the cell membrane. Near the charged drum of a photocopier, 10 to the 5. Near a plastic comb that you've rubbed against your hair, 10 to the 3. About where we are, about 10 times smaller than that. Typical fields of about 100 newtons per coulomb. And inside a copper wire, which is a very good conductor, it's very small, about 10 to the negative 2 newtons per coulomb.